Hey, Psych230. I just wanted to go over the muddy points for ANOVA, analysis of variance. So in terms of what I was seeing, one thing came up a couple times was, it's a lot of formulas, and there's all these new symbols. There's a lot of subscripts. ANOVA looks a lot worse than it ultimately is, and it's because we have like the words between, or the abbreviations for between, within, and total in subscripts. You've got ones and twos and threes and subscripts for the sums of squares and means and all t's and all these things. So once you get used to the subscripts, hopefully you find it a little bit easier. I also just want to point out, I used to teach 3 different versions of ANOVA in this class, and I've dropped 2 of them, and that's when I ended up throwing in chi-square instead. And those other 2 versions of ANOVA get even longer, so they're kind of crazy, but ANOVA definitely is our longest of the test statistics. And it does have all these different symbols and so on. So one of the things, just to reassure you, is that this is the longest that we're going to do. And then when we get to correlation and chi-squared, they're very short in comparison, and shorter than even the t statistics, I think. But I think the other thing that I wanted to point out is, a couple places it showed up here too, is that, you can make a mistake early on in an ANOVA and it will throw everything off. So if you get one of your sums of squares wrong, it throws everything off. And so just a reminder to, again, when you're doing WebAssign, enter your answers one at a time, so you can hopefully catch something like that before it affects everything after it. So that way you might only lose 1, maybe 2 points on the problem set total. Let's see. It took me a while to realize why my numbers for individual sum of squares were so big. Got confused and finally figured that you have to do the big sum of x squared. So we should probably have a symbol for sum of x squared. But anyway, I do again want to point out that sometimes with ANOVA, we, again, usually use examples that have smaller numbers, usually single-digit numbers in our data. That just keeps our math easier, less numbers to work with. But in ANOVA, you'll sometimes get very large numbers, and it all kind of depends on how big the numbers are that you're using from your data. So just know with your project sometimes, some people are measuring days a week exercise. Okay, that will be nice, usually single-digit numbers. Some people will do minutes a week exercised. Then you're going to have very large numbers. Some of your sums of squares will end up being in the millions and trillions and so on. So it can look a lot different than what you're used to. It doesn't mean you made a mistake. I'm still unclear on what the range of F to make it significant. Okay, so with the F ratio, one of the things that I want to remind you is that it's the same kind of idea that we did with the t statistic. What is our critical region cutoff for an F ratio will depend on the degrees of freedom. And so the shape of our curve changes with the degrees of freedom. But first off, the shape is also different than anything we've done so far. The shape for our F ratio is a positively skewed distribution. So if I draw it, our F ratio looks roughly like this. I never get that right, okay? So, and that's because F ratios where there's no treatment effect tend to center around 1. So you can see that we have, think of these again as a bunch of F's stacked on top of each other. These are all the F ratios we could get at different levels. So there's a little bit fewer up here and very few up here, and so on. So these F's down here are consistent with the null hypothesis because they're close to 1. Okay, so then we get to our extreme F's. Everything to the side, to the right here, is our critical region. Okay, so this might be an F of 4 or 5 or 6 or something like that. And so anything out in this shaded region would be considered an extremely large F ratio if the null were true. To be an extremely large F ratio if the null is true is kind of going against the null. And so that's why we reject the null. The null believes that there's no treatment effect, so if we're going against that, we're saying there's probably a treatment effect. So to find this number here, we have to use our F distribution table. Okay, so this is table B4 in our packet. And the tricky thing here, so again, you see the picture that we're working with. It's a skewed distribution. The one really nice thing about the F ratio, you only have one tail. There's no two-tailed option. So you can only have, because all F ratios have to be positive, and that's because the F ratio is two variances divided by each other. And variance has to be positive because variance is the average of a bunch of squared deviations. So squared numbers are always positive, and if you average positive numbers, you're going to get a positive number, and if you divide two positive numbers, you get a positive number. So that's why F ratios have to be positive. Now the trickiest thing here is that we have two different degrees of freedom to look up. There's degrees of freedom numerator and degrees of freedom denominator. So one of the things you can remember is degrees of freedom numerator is always, for you all, degrees of freedom between. So I just do the B/W for between. And then degrees of freedom denominator is degrees of freedom within. Now, the reason it doesn't say degrees of freedom between here and, degrees of freedom within here is because that's not always the case for other versions of the ANOVA. Okay, so if I taught you these other versions, you would learn that eventually. But so you all don't have to worry. So you could almost just replace degrees of freedom numerator here with between, and degrees of freedom denominator with within. And so let's say we had a study that had, let's say, degrees of freedom between of 3 and degrees of freedom within of 18, and we were doing an alpha 0.05. Okay, so that's what we have to find, is we have to find the critical region cutoff. We need to know the alpha, and we need to know the 2 degrees of freedoms. All right, so we've got degrees of freedom, I'll try and show as much as I can here. Degrees of freedom 3 is our between. So up the top here, we're going to go 1, 2, 3. There's the degrees of freedom between. That's our degrees of freedom numerator. So there's our 3. So we're going to be in this column here. So we're going to get our F ratio cutoff somewhere in this column. Now, degrees of freedom denominator is our degrees of freedom within, which is 18. So we can again go to degrees of freedom denominator and find 18. And there it is at the very bottom. And then we go across to that third column over, because that was our degrees of freedom between of 3. And we see 2 numbers. We see a 316 and a 5.09. 3.16 and 5.09. We're going with the 3.16 because the top number is the alpha 0.05. The bottom number is the alpha 0.01. And just in case you forget, that says that right up here. Bold is the alpha 0.01, and then the light face, not bolded, is the alpha 0.05. So ours, again, way down here was 3.16. So what we just found out is that this is 3.16. That's the cutoff for a critical region. So when we eventually calculate our F ratio, and we do our mean square between over mean square within, if that number is bigger than 3.16, we're going to reject the null. If it is less than 3.16, we're going to retain the null. Okay. So again, it's always that cutoff. So let's say our F ratio was a 4.27. 4.27 would be up here. It's above 3.16. So we're going to reject the null. Okay, so that's how we find it. So hopefully that answered that question. Let's see. Number of steps. So many steps. Have to take my time. Again, just remember to enter your answers one at a time. Assumptions and post hoc tests. Don't worry about those. Not going to be tested on it. So if you're confused on that, that's okay. The assumptions are just always there to just remind you that all of our test statistics have assumptions that ideally need to be met. If they aren't met, then it calls into question how accurate the statistics are. So it's, again, statisticians have to kind of keep track of that stuff. You guys don't need to. And then the post hoc test is just to know that when we run an ANOVA, let's say we're comparing 3 or 4 groups to each other. When we run an ANOVA and we get a statistically significant result, all we know from the work we're doing in this class is that there is a difference somewhere in those 4 groups. We don't know where or how, because it could be that the first group is higher than all the other 3 groups. It could be that the first group and the second group are higher than the third group and the fourth group. It could be that the first group is higher than the second group, which is higher than the third group, which is higher than the fourth group, all at statistically significant levels. We don't know any of that from what we're doing in this class. All we know is that there's a difference. The post hoc tests are where you test for the specific differences, and that's more calculations and so on, and we're just not going to worry about doing that. But when you read literature results, you might run into that, and so just know that's what that is. That's that secondary phase when we're running an ANOVA. And then the last thing here, muddiest point with this ANOVA is getting confused with the 3 variations total between within, but with a bit of practice it makes sense, especially since we can proof it if we are right. Within plus between equals total. That's, again, one of the really nice things, and I always try to show you where you can check your work. So yes, your degrees of freedom within plus your degrees of freedom between should equal your degrees of freedom total. Your sum of squares between plus your sum of squares within should equal your sum of squares total. Now, I will warn you that with degrees of freedom, you can still have a calculation error and they will add up. But with sum of squares, it would be very rare to get them to add up if you made a mistake. But with degrees of freedom, it's not hard, and that's partly because sometimes people get k wrong. So if you're subtracting by the wrong k, yeah, it'll add up, but your degrees of freedom total and degrees of freedom between will be wrong. So that's just something to kind of keep an eye out. But again, I do think it's really nice to be able to check that work. Okay, so that is all really I saw here that I wanted to go over. Again, it is just a lot of calculations. So just try to, keep track, and, for the test, just have, for any of you, we've got these 3 tests or 3 statistics left, the ANOVA, the correlation, and the chi-square. I would have a problem worked out start to finish for each of those 3, and then with the chi-square, you want 2 versions of it because you're going to see that there's 2 versions of chi-square. Do that and have that somewhere handy for your test so that you know exactly what to do once you get to that test, or get to that part on the test. So if the test is on ANOVA, okay, here's my ANOVA one from start to finish, and just follow it. All right, so good luck.